In this video we're going to talk about something called standing waves, which is related to resonance, something that we studied with simple harmonic motion. So hopefully you've seen the video on the Tacoma Narrows Bridge from simple harmonic motion, and this is really pretty much the same type of a thing. What we saw in that video were standing waves, and we're going to be focusing on what standing waves are. First of all, the idea of what standing waves are is pretty simple. What you have is you have interference patterns that do not change. So in one of the Falstad simulations, it looked like the interference pattern might have been changing or fluctuating or oscillating over time. With a standing wave, what you get is the same thing all the time, or at least the same pattern all the time. You might get a crest and then a trough and then a crest and a trough and so on, but you have areas of constructive interference that occupy certain spots in space, and you have areas of destructive interference which occupy certain spots in space, and those spots don't change. When we're talking about standing waves and resonance, oftentimes one of the primary reasons why we have the interference occurring is because of reflections. And I'll show you some examples of that. Another thing is that, or really what gets at the heart of why standing waves are important and why resonance is important, is because when you have standing waves, when you have resonance, there can be an energy buildup. And just to highlight what resonance is again, resonance is when there's a driving frequency that matches the frequency at which the object wants to vibrate. When we call that normally the fundamental or natural frequency of the object. And standing waves, the reason why we treat them with such importance is because they're absolutely crucial to understanding how sound is made and how music is made. So what I'm going to do now is show you an example using the wave simulation from PhET. Okay, so this is that wave simulation. Let me get this recentered. Alright, here it is centered. And I have it at an amplitude of 50 and fluctuating 6 times every second. Obviously it's not real time 6 seconds. And zero damping, high tension. And what we see here is that there are times when it seems like maybe it's building up a little bit. It's getting us, like right there, we had a pretty big amplitude. And then once we get this big amplitude going, it seems like it starts to cancel itself out. And you get to the point where, like that last little segment, there's actually nothing happening. That's a case of complete destructive interference. And one of the keys is that you have this guy right here causing an oscillation, at least an initial oscillation. And you also have a reflection. So let's look at this for a moment. What's going to happen is, let me get one that looks pretty good. Right here. So what's happening is this wave is now traveling, you could say that this wave is traveling to the right. And what's going to happen is, as that wave travels to the right, it's going to get here, and it's going to get inverted by the fixed point, by the fixed end. So it's going to start coming back inverted. Meanwhile, this generator, the oscillating source, is going to be not quite on its way down. It might still be a little bit up above here. So what's going to happen is it's going to be generating a wave that's not yet underneath. And so the end result is that there's going to be some constructive interference, because it's not really in opposition, but it's not going to be truly constructive interference. And hopefully you can see that occurring now. As this wave gets reflected in, this one's starting to make, the fixed end is reflecting an inverted wave, and there was still actually a forward moving upright wave coming down. And so the result is that they're canceling each other out. What we'll see as we continue forward is that we get to a point where they do add together. But then they do start to cancel each other out again. So the question is, what can we do to change this up a little bit? And I'm just going to do a small change from 6 Hertz to 8 Hertz. And I'll reset this. And now when you watch it, it's lining up much better. So as the reflection comes back inverted, And you can watch this one. So right now, this is in the midst of just getting a wave generated. So it hasn't quite formed the wave pulse yet, but it's about to form a wave pulse that's inverted coming back. And we just had a wave, an upright wave, come down. So this fixed endpoint now is in the process of making an inverted wave to come back. So we have, from both sides, an inverted wave forming, or just about to happen. And so the end result is that you get a large inverted wave, and then it oscillates back and forth. So the reflection and the wave being generated by our oscillating source are matching up with each other. And we have this very high energy now wavelength, wave amplitude. But this isn't the only standing wave that I can generate given this amplitude and that frequency and so on. One of the things that we can do here is now if we double this, and bear in mind that we're not getting perfect results right here. So it turns out that 16 isn't quite double. I think 17 is the right double for it. But here we have this thing now, and it seems to be oscillating with this green point in the center ultimately kind of staying right around the middle point. You can see these other ones. For instance, this red ball right here, if this is attached to a spring, this red ball right here, it's just maybe a particular set of coils, and it displaces from the equilibrium, from this no displacement line, by a lot. Not just negatively, but positively as well, and it displaces a lot. This green ball here displaces by this much at the most. We call these areas where there's no actual motion or very, very little motion, we call them nodes. And so we should be able to actually make this pretty much stationary and get some good oscillations around it. This is obviously stationary. Another thing that we can do though is we can take this and we can completely get rid of the amplitude that this has. So it's staying in place. So here's a node, here's another node, and here's the final node. Now obviously in a real system there would be some damping, and so this would eventually peter out. But because it's at a resonant frequency for this string, it's actually going to be able to persist for a while. So let me just give this a damping of, let's say, 6. And you can see it's persisting. It's not that it's going to continue indefinitely, but it is persisting in the same pattern for a while. And that's unique to standing waves, both the level of the persistence, because they were able to store up so much energy without changing the oscillation amount, and also the fact that it'll persist for a while afterwards. I want to just bring your attention to that again. So here's this amplitude of 50. Now if I continue to raise the amplitude, if I just keep oscillating bigger and bigger, what will happen is you will get a buildup. You will get waves starting to form that are bigger and bigger. The problem is that it's not sustainable. It's going to go away unless the frequency is right. So I'm going to do another frequency here, and we'll see if this one works out a little bit better. So you can see it's not quite perfect. It's not quite lining up perfectly. And we are getting some buildup of the waves. They're getting much, much larger now. And so this would be another example of a standing wave, or a wave that's oscillating at a resonance frequency. And these green balls here, this time, they're really staying very close to the center. Now there's some other things that we can look at with this. So one thing to look at, and I'm going to try to get us a good spot for it. Now it's not going to be easy to get. Wow, there's a lot of energy involved here. It's going to be difficult to catch them, so I'm going to reset it, and we'll look at it before it gets out of control. So we have a node here, here, and there. So that's 3 nodes, and this one, all I have to do is decrease the amplitude to 0, and now we'll have 4 nodes, essentially 4 nodes. That does leave us, however, with some antinodes, and the antinodes are areas of maximal displacement. So this represents one antinode, this represents another antinode, and this represents the third of the antinodes. So in this case, there are 3 antinodes and 4 nodes. If we looked at the previous case at about 16 to 17 hertz, we saw 2 antinodes, and you can convince yourself of this by going back and looking. We had 2 antinodes and 3 nodes. If we go all the way down to the initial set that gave us a resonant frequency or a standing wave, it was about 8 was the frequency, and there was only 1 antinode, the big one that stretched across the center, and 2 nodes. So what tends to happen is that every time you add to the frequency the initial increment of the frequency, what's going to happen is you're going to get another antinode. Oftentimes we call that initial frequency that you saw the fundamental frequency, or the first harmonic, and it has 1 antinode for the first harmonic. This would be the third harmonic, and there are 3 antinodes. So hopefully you can see the pattern that's going to be forming in terms of the wave structure, the number of antinodes, and how many multiples of the original frequency we've done in order to get to this point. That's going to be it for this video lecture. I might start off the next one with a little bit more on standing waves and resonance, just to make sure that the point is clear. And then we're going to move on to another example of how important interference is for something like music or sound.